Chairman of the board of the SETI Institute. And before I introduce our illustrious panel members, I'd like to remind you of two things. One is that we're selling DVDs in the foyer over there of all of the panels and all of the fireside chats. We urge you for $10 a piece to go buy the ones for the panel discussion that you missed, because we all know that it's been an embarrassment of riches, where at the same exact time we have, at least all of us, I know there was not a time in which there were at least not 2 or 3 competing events that I would have liked to have seen. Unfortunately, I'm not able to divide myself. Consequently, I want to go out and get the DVDs of the ones that I missed, and especially on this panel, you're going to want to, even when you're here, go pick up the DVD of the one you were at so that you can experience it again and again, as they say, and bootleg it on the internet or whatever. Okay. The second piece of house cleaning has to do with the topic at hand, which is the future of the ATA. The future of the ATA, they will discuss. But I'm going to tell you, as the business guy in charge, that the future of the ATA and the future of SETI at large depends entirely upon the generosity of individual citizens who care about the science that we do. We do not receive any government funding, or virtually no government funding for SETI research. So your help, the public's help, is encouraged all the time, please. Okay, future of the ATA. To my immediate right, your left, is Jack Welsh, the Professor Emeritus of Astronomy at UC Berkeley. He's a specialist in the formation of stars, dark dust clouds, the Michelson interferometer array, and he is the chief designer of the Allen telescope array that we're about to discuss. Furthermore, he is none other than the husband to the illustrious Jill Tarter. To his right and to your further left, Jill Tarter. Do I need to introduce Jill Tarter? Okay, I will. I will, just in case that one of you just landed here from another planet. Jill currently holds the Bernard Oliver Chair for SETI Research at the SETI Institute. She is the heart and soul of SETI. She's listed by Time magazine as one of the most 100 influential people on Earth, recent winner of the prestigious TED Award. She was the original inspiration for the character played by Jodie Foster in the movie Contact, and our personal inspiration at the SETI Institute, and she even has a special room named after her at the SETI Institute called the Jill Tarter Inspiration Room. Now, Jerry Harp, to her immediate right, just took recently Jill's other title at the SETI Institute. So Jerry has been promoted. Jill was, and now Jerry is, the head of the director of our SETI Research Center, or the Center for SETI Research, which is one of the 3 divisions of the SETI Institute, the other being the Carl Sagan the Center for Astrobiology, and the third being our educational and outreach work. So Jerry was originally trained to be a quantum mechanic. Was that a Ford Quantum or a Chevy Quantum? Okay, I can't remember, but he was trained to be a quantum mechanic, but he was lured to the SETI Institute because of the ATA's intriguing possibilities, of which he'll discuss today. He's undertaken many studies of beam formation. Now, what is beam formation? I think you'll tell us, right? Yes. Sure. Okay. Good. And he's particularly which is particularly useful in canceling out or rejecting signals from such man-made noisemakers as telecommunication satellites and on-site observatory computers, or that cell phone in your pocket. Anyway, opening statements. followed by, we'll have you comment on each other, and then we'll open it up to some questions. Is there a future? What is the future of the ATA? What is the ATA? Does everybody know what the ATA is? Yeah, anybody? No, seriously, don't be embarrassed. Anybody not know what it is?
Well, why don't I start
All
with
right,
that?
please. Okay.
All right. The ATA is the Allen Telescope Array. Allen is after Paul Allen, the co-founder of Microsoft, because Paul was brave enough to fund the technology development of this new type of instrument and the first phase of construction. Now, currently, the ATA was designed to have 350 small, that's 6-meter antennas, all hooked together with an impressive amount of technology and networking gear to work as the equivalent of a single dish that's about 114 meters in diameter, but a single dish that has a much better ability to resolve small things on the sky, because as opposed to being one thing, it's many small things spread out on the ground, actually over almost a kilometer. Now, today we don't have 350 telescopes. We have 42. Why 42? Because if you're going to stop anywhere short of 350, 42 is about the other best number in the world. It's life, the universe, and everything, right? So we have 42 small dishes, a large number of small dishes. This is the first time an array has been built in this manner. It is incredibly agile. It has the ability to look, because of the small dishes, at a very large area on the sky at one time. And there are many interesting things going on in that large patch of sky. So if you're willing to share the sky, there's the ability to do up to 4 completely separate, independent observations at the same time, because this telescope has 4 data paths that you can use simultaneously. As you'll hear, 2 of those paths have traditionally been populated by imaging correlators. Jerry will explain that. And 2 of the paths have been populated by multiple beamformers. Jerry will explain that. But it is a marvelous telescope for surveying the sky. And I think, as Jack will explain to you, your ability to survey the sky is numerically estimated by the product of the number of dishes times the diameter of the dishes. And even with 42 telescopes, this is a mighty survey instrument. We, of course, would like to grow it further, and more dishes will be better. So the question is, where do they come from? Well, I'm hoping that some will come from individuals. It's not cost effective to build telescopes except in sort of batches of 30 or 40. So we need to aggregate funds to be able to build the next step. If we were to go to 128 dishes, this would be a world-class instrument, absolutely. 350 gives us about 10 times the sensitivity that we have now, so that we could hear fainter signals or the same intensity signal from farther away by a factor of 3. There's also other potentials for expanding the number of dishes. We are doing work through SRI International, who has contracts with the Air Force for doing space situational awareness. That's tracking what's going on up there. Turns out that this telescope has some unique characteristics that are extraordinarily good for this job. So there may be an opportunity, by working with the Air Force, to expand the array. The array really should be in other locations around the world. We certainly would like to have one in the southern hemisphere. There's an Air Force project to build a radar fence, essentially across Australia, around the equator, to track debris. maybe there's an opportunity for these technologies that we've developed, which make it very cost-effective to build these telescopes, to be incorporated into that. Ultimately, where I think we will see many more dishes is in an international project called the Square Kilometer Array, which has been going on since, as a grassroots astronomical project, since the early 90s. And I was just looking back a couple of days ago at some early work trying to be innovative. The astronomical community around the globe tried to figure out how to build a huge collecting area, 1 million square meters of collecting area inexpensively. And there were, remember the Lüneburg lenses and an aerostat, an airborne balloon that held up a receiver structure for a big flat telescope on the prairies of Canada, all kinds of different ideas. And guess what it looks like now? It looks like the ATA on steroids. Mm-hmm. So we have pioneered this large number of small dishes. We've sold it to the world. And if the Square Kilometer Array ever gets built, it will be, in effect, the next generation of a whole lot of ATA dishes.
John?
No one wants to follow Jill.
But you are. And I'm so glad.
I do, yes.
And I'm so glad.
All right. What I want to tell you about the ATA is where it fits in the plan. And we do have a plan. And I can start by sort of telling you a little bit about the development of telescopes. And this is sort of true for all kinds of telescopes, for long wavelength array or radio telescopes to centimeter wavelength radio telescopes like ours, millimeter wavelength telescopes like ALMA, and then I'm going to just skip all of the rest to get to optical instruments. The development starts with just sticking a single probe out there and looking for light. It could be radio waves, it could be optical light, but it's all light to a physicist. And what does a single probe give you? It gives you the ability to receive signals from almost every direction at once, except the stuff below the ground, which you can't see because you can't look through the earth. The next thing that you want to do is that you get tired of that because, first of all, you don't know where any of the signals are coming from. You'd like to know, you'd like to make a picture or something. And furthermore, you don't have very much sensitivity. So the next thing that you do is you build a mirror, a curved mirror, and then you put your probe at the focal point of that mirror. And then you have the collecting area of the mirror, and you have directionality from the mirror because the mirror only collects waves from a particular direction. And so that works pretty well, and that's what you might call a single dish radio telescope these days. The next thing that you want to do is have more mirrors. You find at some point that there's only so big of a certain mirror that you can build, and beyond that point, it's impossible to get the mirror perfect enough over very large distances. So what you do is you start breaking the mirror into pieces. And you could look at large optical telescopes today. They're not actually made of one giant mirror, they're made of a bunch of little pieces. Same thing is true of millimeter wavelength telescopes in many cases. What do you do after that? Well, what you do is you take all those individual mirrors and you make them even bigger, and you give up on the idea of having them all focus on one point. So you have many, many mirrors on the ground, and they all have their own receivers. But then you've got a big challenge, which is to take all that data from all those different receivers and somehow put them together in a way to get what you're looking for. And so what's happening? As we do all of these things, we get a mirror, we can only see in one direction, we build an array, and our resolution gets a whole lot better, but we only see in just a tiny, tiny little bit of the sky. And so what have we given up? We gained the sensitivity, but we've given up the ability to see everything. And now we only just see a little bit of something. So the next step then is to use the array that you've already built, but use even more computation, orders of magnitude more computation, so that with the mirrors on the ground, you can start to see individual stars within the field of view. And so you start to pixelate the field of view. And that's what the ATA is. That's where we are right now, which is that we can look at a fairly good hunk of the sky because we have small mirrors, and we have this antennas spread far apart from each other, so we get something like a 50 by 50 pixel image anytime we look with the telescope. And then finally, what you do is that you leave all the sensors in place and you throw away the mirrors. You just build a lot more of the sensors. Now, this becomes a real computational headache. But this would be an omnidirectional telescope. It would see everything at once, and you could see exactly where everything is coming from. And it would be very, very, very sensitive. Now, the omnidirectional telescope is the endpoint that we've thought of so far of telescope building, and this is this whole timeline for SETI, at least, is outlined in a book that you can go and buy at the SETI store. It's called SETI 2020, and in that book, it talks about where we were 15 years ago, and it talks about the ATA as a middling step, because now we're getting many dishes on the ground, many mirrors on the ground, and they all have different receivers. And so that's on our way eventually to the omnidirectional array. Now, I've been promised that I would tell you what the difference between a beamformer and a correlator. So the beamformer and correlator, you can think of them as two steps in the direction toward getting an omnidirectional telescope. The first one is the beamformer. So you take all of the dishes on the ground, and you basically point them all at the same place, and you phase them up, we say. Basically, you focus the telescope so that they are sensitive in only one tiny direction. That's a beam. And it has the resolution of the array. It's a big array, so you have very good resolution, tight resolution. But again, you only see that one point. Now, at the ATA, we have 3 beamformers, so we can see 3 points at a time, which is really cool, which is really amazing. And we use those different beams against each other to figure out if things are RFI or if they're actually coming from outer space. But then there's another processing system at the ATA, which is called the correlator, which is very technical. You can just think of it as an imager. Basically what it is, it's instead of just having a single LED light sensor behind a lens, you put a whole bunch of light sensors behind the lens, and like your camera. And so with the same computing power as we use for the beamformers, we can construct an image of the sky. In other words, 50 by 50, 2,500 pixels or so, depending on how you count, of information that we can get from this telescope. But as you can imagine, if you're going from 3 beams to 2,500, there's a big step in computation. And because right now we're limited by our computational abilities, the correlator has to give something up, and that is the frequency resolution. So what does that mean? That means that you can, with the beamformers and our instrument on the back of the beamformer, we can see colors to exquisite detail. And I'm not talking about real optical colors, I'm talking about an extension, an analog of color into the radio range. So we can pick out precisely, very well, a certain frequency, a certain color of the radio waves that we can discover, and therefore be very sensitive to these narrow color signals. And that's what SETI does. That's sort of the main line of what SETI does. The correlator, on the other hand, does not have the same color resolution. It's got sort of a wide resolution, but it does have the ability to produce images every 10 seconds. So I'll just leave it at that.
Jack?
Okay. Well, let me pick up on this idea.
Grab a mic.
Yeah. say a little bit more on this idea of the sensitivity when you have one or many antennas. How are you doing? Can you hear me now? Okay, good. Okay, you could imagine two extreme cases. You want to look at something that's out there with the best sensitivity you have, so build as big as an antenna as you can. This is just picking up from what the others have said, like the Arecibo telescope, which is roughly 300 meters across. And it focuses on a small region of the sky. And if that's the only part you're interested in, that's the best telescope to build, because then you just need one simple receiver at the focus of this thing. Can receive all the signal from that one small object. If you want more sensitivity, you can make it bigger, okay? But of course, as you do that, the resolution goes down. The size of the spot you're looking at gets smaller and smaller. If that spot gets to be smaller than the region you want to study, then you have to be prepared to steer the telescope around, right? To point to these different spots at different times. And so that's the way you do that. Okay, now the sensitivity for this system is proportional to the area, so that's proportional to the diameter squared. Now, if on the other hand your program is to look at a lot of different spots, then as you think about how to decide on the size of the dish, it's a little more complicated. If you have to steer the big dish around to many positions, that means you can't spend very much time on any one of them, okay? So then you think about, well, maybe what I should do is to make a smaller dish, then it looks into a bigger angle, and then when I've done observing for some length of time, it's not so much diluted because I have to look at all these different directions. And so what we've done here is to build this kind of dish, or kind of system rather, which has many, many different dishes. And this allows us to spend less time, or rather more time, I should say, with a given pointing, on one part of the sky. And so it turns out that the sensitivity, if you work it out, depends on the number of dishes and the size of the dish, and it goes as not nd squared, if you're just pointing in one direction, but rather n times d. The reason for that is that when you have to do many pointings, you have very, very much less time on any one of them. And so sensitivity ultimately then is the number times the diameter. So if you start making comparisons, then where are we? Let's take the Arecibo telescope. It's about 240 meters across. There's one of them, so ND is 240 meters. For the ATA, our dishes that we use are many but small, so they're 6 meters. And for the ATA, ND is 6 times 40, that's about 240. And ND for Arecibo is 1 times 240. It's the same number. Okay? So if your program is to do a large survey, you have to think carefully about what kind of instrument to build. And so we've generally gone in the direction of saying we're going to do surveys. Surveys are done best with many small dishes because it's ND. And the example I picked, the Allen array is just as sensitive as the Arecibo telescope. Or if you take the 100 meter at Green Bank, that's another big dish that we have in the US. That's 1 times 100. That's actually less sensitive if you're doing surveys than the Allen telescope or the Arecibo telescope. So surveys are it. Why do we know that so for the for trying to find the SETI signal? Well, we now have good candidate locations to look at. These are the Kepler stars, and they're spread out over a huge range of sky. To look at all of them is certainly a big survey. So we want a large number of small dishes to do that. And that's basically what we have. And so we have about the same sensitivity as any other dish out there already, with only 40 of these. So the direction we're hoping to go is to have more dishes, and that's something that we hope will come about. We're not sure where exactly we'll get the support, but as Jill says, we're actually doing some work for the Air Force and having a big array with a lot of resolution or a lot of point source capability is a good thing. So we're in the right domain. So the direction we're hoping to go in is to get more dishes.
How about more frequency?
And that's the other one. There's another dimension, more frequencies. What sort of frequency range do you want? Well, if you know what it is that you're going to look at, that it's a particular frequency, for example, it's a GPS satellite at 1300 megahertz, you can have a rather narrowband receiver on your system, so you can follow it that way. But we're doing many satellites, but even more to the point, we're looking at a whole range of frequencies in which we might find a SETI signal. So what is that range? It's roughly 1 to 10 gigahertz. That's the transparent window through the atmosphere, fixed on the bottom end by the background from the galaxy, and on the top end from the water vapor and the oxygen. And so that's the range we want to study. That's a huge frequency. If you have a narrowband receiver, then it's like poking around with a narrow beam on the telescope. You have to tune many, many times over. So we're also pushing in the direction of having huge bandwidth for the receiver. And even now, the bandwidth is quite large. The single receivers on the telescopes operate from half a gigahertz, that's 500 megahertz, up to about 10. So that's most of this range, but not quite all of it. We're also working on improving the receiver. In fact, we've made a big breakthrough in that recently. And we're building a receiver now that will work from about 1 gigahertz to 15. So it completely fills in that window. And so we've got this one unit done. And not only does it give good coverage, better than we have at the moment, but the sensitivity is 2 to 3 times better than, than what we've had. So we have with this new receiver a factor of 2 to 3, and it's as if we had 2 to 3 times as many antennas. So that's a big plus. So what we're looking forward to in the near future is, for the 40 antennas, being able to put one of these new receivers on each. So that'll be an important development. That'll give this a sensitivity as if we had doubled or tripled the number of antennas.
Can you talk about rough cost estimates for batches of dishes, the entire complement of 350, and the upgrades of the feeds? What sort of money are?
Well, for the feed, we know that the new feed, if we can do this, will cost about $3 million to put it on every one of the 42 antennas. So there's a number. And then, of course, if we have more antennas, perhaps doubling the number or tripling the number, so we would have 130 or even 256, the costs go up proportionally for that sort of thing. And so that's the direction we want to go in. More antennas, more bandwidth. We've already found this very good receiver to do that. And so we're optimistic that that'll be a big help. So we can cover all the possible frequencies in which we expect to hear anything, fixed by our atmospheric window. And so the frequency part we have covered with this next development, and then the next step forward will be more antennas.
And John, you asked about the cost.
Right.
So Jack is talking about maybe $70K per antenna
On the feeds.
on the feeds.
Right.
If we were to build new antennas in large batches, it's like $180,000 to $200,000 an antenna. So at least at first, for outfitting 42 antennas with new feeds, you get the effect of having the sensitivity of 84 dishes, but at only about 1/3 the cost. But ultimately, we want to build more dishes. We want to fill the valley in Hat Creek with dishes.
Do any of you want to react to any of the others or make further comments?
I have a small addition. Jack has outlined many of the ways that we're planning to improve the array in the near future, and the first of all would be to perhaps replace all the feeds, all the receivers, with the new design that was basically done by this man right here. And it's a fantastic receiver. I'm looking forward to that. Testing is going on right now, or these days. The next thing that we might do would be to move the antennas that we have to be further apart from one another. Now, why would you do that? It's because it would give you more pixels in your picture, right? The larger the diameter of the array, the better the resolution. But the field of view is fixed by the antenna diameter. So you move them further apart, the field of view doesn't change. So what we get is more different pixels that we can measure at one time, so we get more resolution, and that may be an advantage. And that's another few $1 million prospect. Besides building more dishes, there is one other thing, though, that we want to upgrade very soon. You know, Jack has already designed and built this fantastic feed, which is really unique. It covers 4.5 octaves of radio frequency range, which is practically unprecedented in a dual polarization instrument, and this is patented. So we have all of this frequency available to us, but we have 4 100 megahertz, let's say 0.1 gigahertz bands. So we have 10 gigahertz to look at and 0.4 gigahertz that we can actually measure at any one time. So if we could improve the computing power at the array and upgrade the correlators, upgrade the beamformers to have more bandwidth. Now this is very wild guess. I'm guessing it's on the order of a couple $1 million. So we could go up to perhaps a gigahertz times 4. So improve our data throughput by a factor of 10 with something on the order of a couple $1 million.
And why would you build, why would you want to build in the southern hemisphere? You don't have enough stars in the northern hemisphere to do your SETI search, or
Well,
have you run out already, or?
not yet, but the center of the galaxy is in the southern hemisphere.
Mm-hmm.
And if we want to say, take the approach that, well, after all, every star has a planet, then if you want to look at the largest number of planets, you look at the largest number of stars you can. And if you were to scan 20 square degrees around the center of the galaxy, so plus and minus a degree above the plane, and plus and minus 5 degrees from the galactic center. So this 20 square degree box, you'd actually be interrogating somewhere between 4 and 10 billion stars.
But we can see the galactic center from the Bay Area. It may be above the southern hemisphere, but we can see it.
We can, but only for a few hours of a day. So if you were to try and decide that your next search strategy is one that wants to focus on the galactic center region, a southern hemisphere telescope would be very important. Southern hemisphere telescope is also important in terms of space situational awareness. So that there might be some desire to do that from the Air Force point of view. I need some water.
All right, so so one of the things that you would like to do in the future is build well, we've talked about the build-out a little bit, but let's talk about the experimental paradigms. Why don't you tell us a little bit about how you're using the ATA today? What are you doing with the ATA? What's your experimental paradigm? And what future methods you might be using to expand the paradigm?
Well, I'll start with what we're doing today.
Sure.
And Jerry can talk about what he's going to start doing tomorrow. So at the moment, most SETI programs on the telescopes are saying we want to find deliberate engineered signals. And so what we're going to do is look at what astrophysics does in terms of emission. And we'll look for signals that don't look like that. And so we've come up with 2 solutions. In the radio domain, you look for frequency compression. You look for signals that only show up on one of these 10 billion channels of the radio dial. In the optical, you look for time compression. You look for broad, bright optical flashes that last for 1/1000th of a second or less. Both of these things are done all the time by technology as we know it. They seem to be impossible to achieve with astrophysics only. This has been our sandbox. This continues to be a good sandbox, but it isn't the only thing. And with the advent of increased computing power, there's an opportunity to look for other kinds of signals. And that's what Jerry is going to begin to work on and is already starting with some interns this summer. Do you want to talk about that?
Jerry?
Thanks. There's a reason why SETI has been looking for narrowband signals for a very long time, for 50 years. And the reason is that, first of all, we know now that only very narrowband signals, these sinusoidal tones that can pass through the interstellar medium. I mean, remember, they have to get from their star to our star, so they have to go in between stars. And the interstellar medium has plasma, and plasma distorts light. So if you send out a pulse of light, it may be a pulse at the beginning, but by the time it arrives at the destination, it is no longer a pulse. It's been all broadened out and squiggled in a very computable but not obvious way. So that's one reason. The other reason is that human beings, our technology, especially our computer technology, and I happen to be a computer guy, and I think about these things, the fastest transform of any kind on Earth is the Fourier transform. What does that mean? This is how we make a spectrum from a signal with a computer. And this transform is so fast by many orders of magnitude than anything else we have that it's like looking again, in the easiest place to look. We can get fantastic sensitivity. We can do it very cheaply and quickly with the computers that we have. So that's where you start. That's perfectly obvious. But at some point, computers start to get so good that is no longer a barrier. And because the dispersion that happens, we call it dispersion, but this distortion through the interstellar medium is a computable thing. We know the properties, and with a little bit of fooling around with the parameters, we can undo the distortion of the interstellar medium. So we're starting to think now about other kinds of signals that they might be sending, signals that may contain information. Now, you ask the question, well, will we be as sensitive to those kinds of signals as we are to the sine waves that we've been looking for all along? And the answer is, it all depends on your algorithm, what it is that you think you're looking for. Now, one of the topics that I've been interested in recently is another kind of artificial signal that is not exactly a sine wave. It's actually maybe a very complicated pattern, but the pattern repeats and repeats and repeats and repeats and repeats. And if you had some kind of repetitive signal, it could contain any information, it could be as complicated as you like, but as long as it repeats, then we can look for that repetition in the data. That's all we have to do. And there's a very simple technique called autocorrelation spectroscopy, which you can look up, and it gives you a measure of the repetitiveness of a signal. And so this is one of the directions that we're going to take next. I will make the caveat, though, that although autocorrelation spectroscopy, instead of just picking up just one kind of repeating signal, it picks up every kind of repeating signal. So, I mean, the signal literally can be anything. It doesn't matter. It just has to repeat. So it covers a much broader territory in terms of the kind of signals that may be coming in. But it is inherently less sensitive. I mean, it sort of makes sense. You cover more in one space, you have to give something up in another space. So autocorrelation spectroscopy is not quite as sensitive. But if we find something, nobody's ever done this before, right? So it may be sitting there right under our noses, and we haven't seen it yet because nobody's bothered to look. So this is what really obviously excites me whenever I think about it.
At this point, I think I'd like to open it up to the audience and entertain some questions. Who's got the microphone? Do we have a volunteer? Great. So somebody raise a hand and let's get going. We've got one question up here, right at the beginning, right at the front of the... And if somebody else wants to raise a hand for a question, we've got a second microphone so you can be pre-prepared.
Hopefully this is a quick question. Based on what you just described, do you think as a byproduct you might find, say, a bunch of pulsars or similar phenomena that are natural?
Well, it turns out that this isn't a very good way of looking for pulsars, although you could do that. Pulsars respond, because they're generally weak, you have to do more intensive processing than a simple autocorrelation in order to see them. And that may also be true. But on the other hand, we don't know what we're looking for because we'll be looking at repetition rates that are faster than a pulsar could possibly rotate. Remember that pulsars, by their nature, they're all about the same size, on the order of a kilometer in diameter. And as they spin, at a certain point, the surface of that rotating neutron star is approaching the speed of light. And the surface of that star cannot go any faster than the speed of light. Therefore, it can only spin so fast, something like 100 microseconds period or along those lines. So we're going to be looking in ranges that are even faster than that. So clearly artificial.
So it might actually be less noisy signals that you're processing in that regard.
Next question. Is there somebody else who wants to pre-prepare? There's a question back, way in the back, the lady in the far back. Okay, good. Please, sir.
At the Allen Array, when I was up there to see the eclipse or the partial eclipse, we went in and talked to Jill in the office, and I had one question that I thought of naturally after we left. How long do you look at one particular band before you go on to the next band?
So at the moment, the automated searching that we're doing, and as Jerry said, we only have 400 megahertz bands that we can look through, and we've got 9 gigahertz, 9 billion channels we want to search through. So we typically step up, we typically look at 3 objects, so we can look at 3 planetary systems at the same time, and we observe a particular frequency band for about 90 seconds before we go on up to the next frequency band, and then the next frequency band. And we're doing our signal processing in near real time, so that after we have accumulated the data at one frequency band, and we move up and start taking data at the higher frequency, we also begin processing the data we just took. And by the time the next data acquisition cycle is finished, we've looked at, that is, the computer has looked at all of the signals, classified them as either something we know to be interference we've already seen before on the sky from some other direction, or an interesting candidate to follow up on. And if any of those are there at the end of the second data acquisition cycle, instead of going up to the next higher frequency, we go back to the lower frequency and we follow up and observe. And right now, you were talking, and I was trying to demonstrate to you when you were there, a new project called SETILive.org, which is our attempt to have citizen scientists help us. There are certain bands of this huge spectral region that is available to us that are hugely contaminated with our own telecom signals. So when we do this automated processing, our computers can currently find all those signals. They just can't figure out what they are before the next data cycle has to start. And instead of processing to some indeterminate level within those bands, we just skip them. We say they're too crowded and we are blind there. We're hoping that the citizen scientists, by getting the data raw from the telescope and helping us not only find patterns and strange patterns that we might now be missing, but tell us whether those patterns exist in the other directions on the sky and help us do the classification that is confusing our machines at the moment. We're hoping that the citizen scientists can characterize these crowded bands where we're now blind, and maybe, in fact, tell us that, well, that band is blocked by that satellite, which is only above your horizon a certain number of hours a day. So if you're interested in that band, observe it when that source is below the horizon. So it's a long project to try and have people using their think-ons to help our machines learn to do the job better.
Okay. The next question.
Hi, my name's Jasmine. I've really enjoyed this conference. Thank you so much for holding this. My question was, Ms. Tarter, you had mentioned that there are some international projects that may be helping with satellites, and I was just wondering how connected they are with the SETI project, what countries are particularly interested, or if you're going to be sharing information back and forth.
I'm not sure I understood the question. Are you interested in knowing the countries that are participating in this International Square Kilometer Array building project?
Yes,
All right.
and if they're involved directly with your project, or they're also using it for their own projects.
Well, let
And
me
I want to ask also, as an adjunct to that, is it open for SETI? Can SETI researchers use the SKA, or will it when it's constructed?
Well, one of the key science projects that was used to develop the SKA, determine what its requirements are, and to sell it to funding agencies is a science area called the Cradle of Life. And so that involves studying the formation of planetary systems, studying large biogenic molecules, and actually using many beamformers to do SETI observations. So SETI has been in there since the beginning, but unfortunately, the U.S. is no longer part of that. We backed out last year, having been working since the early 90s, because now they're talking about real money. Now they want to talk about phase 1 of construction, and the U.S. is saying we can't afford to be part of that anymore. But the EU, European nations, South Africa, Australia, Japan, China, Canada, and India, thank you guys, are participating in this, this international collaboration, and we keep agitating to be part of it again.
Great, thank you.
All right, next question. If the SKA is devoid of Americans, where are the SETI researchers going to come from? There are a few outside of the United States, but not that many. So will they allow us to use the instrument even though our government hasn't paid for part of it, or are we just out left in the cold?
John, you're not close enough to the microphone. Sorry. Well, John's question is, if the U.S. is out of the game, where are the SETI researchers going to come from to use the SKA? A very good question. Where is the next generation of astronomers, radio astronomers, going to come from? And it may be, the answer is other countries. If there's a will, all of the research that we've done in SETI is published in the open literature. We actually actively encourage other countries to get involved in SETI. Japan was a recent wonderful surprise to us in honor of Frank Drake's Project Ozma, 50 years. A young Japanese astronomer decided that it was appropriate for him to encourage other Japanese observatories and observatories around the world to co-observe, to have a sequence of projects where we all looked at the same thing at the same time. And this was coming out of Japan, which makes me feel really good. I think we need to get the world involved, John. And if Americans want to use the SKA, I think we're going to have to join teams in other countries.
Well, not just get the world involved, get astronomers involved. You know, what you're looking at here on the dais are some extraordinarily brave people who have risked their careers on a Nobel Prize or a famine. It's a feast or famine in the SETI business. It takes a degree of courage for an astronomer to leave an institution with his doctorate and go into an area that is poorly funded, that has less than optimal opportunities to publish, short of the greatest publication of all times, the authorship of the paper that announces the discovery of contact.
Now, John, I disagree with you. I can't disagree about the poorly funded. That's for sure. And that's what I hope that we can change in the near future by establishing an endowment for SETI into the future, so that the young, bright astronomers and physicists don't have to take that risk of future funding to join us. But there's an enormous publication that comes out of SETI of technology developments. Jack's new feed, the ATA, these were done for SETI, but they have huge applications. The technologies that Jerry's talking about, the new signal processing codes and clients, may have applications elsewhere. So I think people who choose to work in this field are very knowledgeable about the fact it's a big cosmic haystack we're trying to explore, but they also appreciate the satisfactions that can come from doing the job better today than we did a year ago.
We have a question. Who's got the mic? You've got.
You had mentioned earlier the possibility of having more citizen scientists involved. It seems to me that one possible step beyond the Allen array technology is 1-meter dishes, where you would have them be small enough and cheap enough that individual high schools or even individual persons could put them in their backyard, have a digitizer, link them onto the internet, and then use some kind of distributed architecture to be able to turn them into beamforming and correlation processing, etc. Furthermore, it seems to me that the trend over the next 10 years in terms of the large number of processors that are going to be found on your average home PC means that the cost of computing this stuff is going to come down even more. So the question is, would it be worthwhile advancing a proposal for citizen scientists to build 1-meter type radio telescopes at an average cost of a few $1,000s, such that we could mass produce these things and proliferate, essentially turning the entire country into one giant radio telescope?
Do you want to take that, or do you
Sure.
want me to?
I think that's a great idea, and I think it's a idea whose time has come or will come shortly. I'll just tell you one technological hurdle, though, that you may have. The internet has a certain latency about it. It seems pretty fast whenever you're working with it, browsing the web, or sometimes it does. But on the time scale of one oscillation of the light, it oscillates pretty fast. It's actually not very reliable, and so we would need to have, along with each 1-meter dish, we need to have a very good clock. And those clocks would all have to be synchronized, and the data would have to be time-stamped. So that increases the cost substantially. The other thing that you might worry about is the amount of data that you can send back over the internet, because the internet, as we know, is already getting clogged with just YouTube videos. So imagine trying to send back a great deal of radio frequency data. You'd run into bandwidth problems. But there may be a way of getting around this. This is an idea that we've been kicking around, which is to build a sort of a pseudo interferometer where you have antennas distributed across the land, across the United States or the world, and have them measure not the amplitude of the radio waves coming in, but the power as a function of time. And then, because the antennas are very far apart, and say the star's over here, the time of arrival for the one antenna in New Jersey and the time of arrival for another antenna in California is large enough that you can start to say something about, based on the time when they arrived, what direction it must have come from. And this isn't so easy to do with a small array, but if you had a great big array, you might be able to do that. So that's one idea. I think I'll just mention one more thing. I'm aware of a group in India whose name I unfortunately can't tell you right now, but they're selling kits that high schools can purchase for a few $100s that measure gamma rays. And their idea is exactly what you suggested. They're these little gamma ray detectors. You can buy them for about $100, and they're setting them up and looking for doing a kind of worldwide array of gamma ray detectors.
Also, amateur optical astronomers might be able to use photomultiplier tubes to do optical SETI in their own backyards. And I once actually began some discussions with Meade Instruments to talk about the possibility, and I need to actually get back to that and see if there's a discussion to be had there.
Or maybe somebody in the audience would like to help you with those
Please.
discussions.
Oh, my goodness. We could always use the help. One more question here?
So
And
there's
I
been,
think this will be our, yes.
yeah, so there's obviously the talk of citizen science and kind of gamification and other ways to get the public involved and interested. And I was wondering if you had any, been giving thoughts to how you may be able to bring sort of crowdsource funding and microtransactions into funding SETI. There's a lot of people who aren't as involved and obviously aren't giving, either $30 or whatever, or a certain amount a year, but they maybe want to give a couple bucks and maybe get more people in that way.
We've actually been giving a lot of thought to that. We did one experiment last summer when the telescope, the Allen Telescope Array, had to be put in hibernation, and we knew that when we got a new partner to operate the telescope, because we had to replace UC Berkeley, which had run out of funding for operations, we knew that when we got a new partner, we were going to need a big delta on the order of a couple $100,000 to bring our equipment back to the telescope, get it all reworking again, and get back on the air. So we did a crowdfunding website. We called it SETI Stars, and we had stars, SETI individuals, become stars and support us. And we were quite successful with that campaign. But that we haven't yet found the right business model, the right vehicle, maybe even the right game to turn that into sustained funding. So if you have any expertise in that area, we'd love to talk to you, because that is something we're really actively considering.
Unfortunately, I don't, but it was the Allen Telescope Array funding issue that actually got me started thinking about this. So, but yeah, it's something I'm giving thought to of how we might be able to do this.
Okay, thanks.
Okay, one last question, and
Yeah,
go
so
ahead.
I think my question is quite mundane. But going up to the array and seeing it, I was surprised at the pattern of the 40 or 42 telescopes that are there. I wonder why that choice is made, why they are arrayed the way they are.
You mean the actual layout on the ground?
Yeah.
It does look random, doesn't it?
It does, but I presume it's not.
Well, the way it was done is to do a repetitive calculation. We knew we had a boundary within which we wanted to put so many antennas, and there were some things like rocks and so on that you couldn't do that. So we put the rocks into the program and everything else, and then essentially threw all the antenna positions in, like that, and calculated the pattern. And the first go was pretty bad. Then we just started moving them one at a time. And the computer can do this thing since it has infinite patience. And we just kept moving them around until we got the pattern we wanted. And there are many different patterns that would actually give you that on the ground.
So as you add more, when all this money comes in, do you have to move the ones you've got, or you know where they're going to go?
No, we can leave those as they are. Actually, they're a subset of the original design pattern, which was for 350 antennas, which is a much larger region. And this is just a little subset of that. So we can leave those where they are.
Okay, thank you for answering that.
All
Thank you.
right.
Yeah, you can actually do a calculation and prove that for any number of antennas, you can pull a subset out of that original pattern and do as well as you could starting from scratch for that number of antennas. And Jack actually didn't mention the trick here, why it works, and what we were relaxing to essentially with these annealing calculations. We arranged it so if you consider a vector between any pair of antennas, it has a direction and it has a length. So you end up getting a pattern, you want a pattern that has uniform distribution in azimuthal direction, but you want the length of the vector to approach as closely as you can a Gaussian curve. Why a Gaussian? Because the Fourier transform of a Gaussian is a Gaussian. And basically, the Fourier transform of this pattern on the ground tells you what your beam looks like on the sky. And if you want a nice, smooth Gaussian beam on the sky without all of these diffraction spikes and all of this stuff, if you start out with a Gaussian on the ground, you get a beautiful pattern on the sky.
Interesting. Well, let's give our panel a round of applause.
Yeah, I thought you were going to give that answer.
And
'cause that's
thank
not
you
your
all
answer,
for
Jared.
attending SETICon, and I think the panelists will probably be up here for a
did.
couple more minutes
That was
if anybody wants to approach.
But he liked that. He was clever.